everyone. Welcome to another episode of Sound Talk Show. We are going to code Advent of Code. Can you see me? Yes, this is my keyboard, UHK80, Ultimate Hacking Keyboard 80. I have a video review on YouTube about a month or 2 months ago. Check it out. And so we are going to do Advent of Code. Let's see, can you see my screen? So Advent of Code 2025, day 4, take 2. So we began yesterday, but we didn't finish. And we are using Wolfram Language, the most advanced programming language. So we are just going to do exploration starting Wolfram Language. And if you don't know, you can search for Xali Wolfram Language for programmers, complete tutorial from the ground up for programmers. And you can find the download link on wolfram.com/developer. There you can download it for free. It's about like 4 gigabytes or 5. So it's a huge programming language. It's the most high level than by a magnitude than all existing programming languages, such as Python, Haskell, Lisp, Rust, or F#. Okay, so Advent of Code. So let's begin coding. Okay, so start the Wolfram kernel. So begin at 3. Let's magnify. Now, if you are here, say hi. Love to see your comments. Keep the comments coming. Hello, Dois Gap. If you are watching my video offline, play at 1.5 speed minimum or play at twice as fast. Okay, so we're just gonna explore. We're gonna go slowly and have fun. As I go, I'm gonna teach you something about Wolfram language, which is from computer science point of view, it's a programming language based on term rewriting system. It's a term rewriting system. What does that mean? Basically, it just means whatever you type, the syntax, it's all symbolic string. So it's like a string. Then what the Wolfram language do is just keeps transforming the string, the sequence of symbols until it arrives at what you want. So it's in other words, you can think of it as a syntax transformation programming language. That's how it does computation. So in other words, you can think of it as the programming language is just whatever you type, the source code is just string. So you just keep doing regular expression, find and replace. That's one way to think of it. So you have a programming language, your source code is like a string. So what the programming, you just write rules about how to do find replace on your source code. So the source code change to another string, change to another string until it arrives. So that's a term rewriting system. You can look up Wikipedia. Okay. So hello Dosi. So yesterday we began excuse me, Advent of Code. Okay. So the Advent of Code, this annoying Advent of Code, they have problems. So let's turn off the page style, no style. So now it's like simple and plain, and you can magnify it. Okay, so that's Advent of Code 2025, day 4. Okay, so we're gonna continue from yesterday. So let's just start coding. Okay. I'm using Emacs, of course, and all my command calls and function name are shown here. So let's make this that. Okay, just like side type, you can see, I move the cursor so you can see the ping window updates. That's for you Emacs users. Show in browser. Okay, so let's begin coding. So let's go to yesterday. So we need to wait. So yesterday, episode 729. So yesterday we wrote some function that returns that given a matrix, you wrote the function getNeighbors. So getNeighbors of a matrix, and you specify two index, that's a row number and the column number. Then it returns all the neighbors around that cell. Okay, and let's improve on that. Okay, getNeighbors. So hi there. So get so okay, so let's see. So there it is. So here is a matrix there. Can you see it? Okay, video check, audio check. Okay, so let's start to improve it. So first of all, I'm using a block here. I don't want to use block. Actually, let's evaluate this so you can see. So here is the matrix input. In fact, let's delete that. Search for XX. Okay, so let's put the matrix here. So you see, so the matrix is there. So that's our argument, then 2, 2. Okay, so if we run this, it will return 2, 2 is the number 5 in the middle. So it will return 1, 2, 3, 4, 6, 7, 8, 9. Run it. There, 1, 2, 3, 4, 6, 7, 8, 9. Okay. Now, those are from the documentation here. So you need to put a semicolon so it doesn't show the output. Run it. Okay, so you can see, copy the whole thing, go to the Wolfram notebook, select all, paste, shift enter. You see, that's the result. Fantastic. Now let's improve the code. Here we are using a block structure. Block basically means local variables. So instead of block, let's use constant. Okay, actually, let me think about this. So block is for local variables, dynamic scope. So we first of all pad the matrix, but instead let's use width. You don't need block, okay, because we are not changing the variable x padded. Okay, so let's rename that padded matrix. Okay, so that makes easier to understand. Okay, returns all the neighbors of a given cell of 2D matrix. Yeah, so we need to improve the documentation here. So instead of saying cell 5, you should say 2, 2, 2, 2. Okay, then cell 6 would be 2, 3. Okay, so let's improve the document. Okay, something like that. So okay, so what else? So let me so what else you want to do? Now yesterday we have a bug somewhere. So in this example, you also need to say, you see, when, okay, so let me show this example. So copy that, go here, paste it. Now if you say 1, 1, 1, 1, which is the first, and the first on the upper left, shift enter. So you get 0, 0, 2, 0, 4, 5. That's because, copy that. matrix form at that shift enter. So that's a matrix. So if you say 1 here, so the neighbors are 2 4 5. So it returns 2 4 5. That's correct. So you need to say when the neighbor, when the cell is on the edge of the matrix, the neighbors are outside of the matrix is considered 0. Okay. Is that a good result? That's actually not so good, but it works in our case. I mean, but it's not generally a good thing because you might have a matrix that's 0, and so what do? You don't want to return 0 actually, but actually 0 works in our case. So you could add another parameter that says what entity you want to use to represent out of the boundary neighbors. Let's see. How do you solve this problem? I don't know. Well, I know, but okay. How do you want to do this? So you padded it's 0 originally, so you can pad it with a you want to pad it with some kind of special value. Then in the return result, you want to remove those value. Okay, so you want to pad it with a special value. You could use almost anything. You could use a string, but however, you want to avoid whatever you use, you must assume that does not exist in the matrix. So the matrix can be a million by a million. You don't know what's in there. So whatever value, like temporary value, you use to pad the matrix, to pad the matrix. So for example, we did this here. So you can see we did this here. So matrix form, paste that. You see it adds 0 around it. Okay, 0, it adds 0 by default, but can you change the padding value? I'm pretty sure you can. Use a specified padding, yeah. So if you pad it by, so for example, let's say something x string, then you got x, okay? So if you want to write this function in general, whatever temporary values you use, you must assume it does not occur in the matrix. So how do you solve that problem? Well, you can solve that by calling this function unique. Okay, that will return a unique symbol. always. So you can, let's read the documentation. You see unique generates a new symbol. Let's magnify. So 150, 125 generates a new symbol whose name is of the form $sign, a number. Okay, that always generates a unique number. So you can say this example. So you can say copy, paste. So over here, instead of X, you can say unique. Okay, then you get that. Then you need to save the value of unique. So later on, when we define our neighbor, it returns 0, 0, 0 for the neighbor. You can then remove them. Okay, so this more work to do. As far as event of code, we can just use 0. It doesn't matter. But let's do it properly. Okay, since we are just gonna explore the Wolfram language. Okay, so check video, check audio, check. Yeah, am I good? Yes. Okay, so unique returns a unique symbol in terms in the form of $sign something. Let's see what we want to do here. Right, you don't want it to, you see, it returns a neighbor, but you don't want it to return 0, 0, 0, like our example here, So let's do it properly, okay? So let's do one thing at a time, fix it one thing at a time. So here, then width and unique. So unique. So you need X unique equals to that. It generates a unique value, constant. Okay. Then when you pad, okay, so actually you can do this. You see, you need the unique array pad. You need to put a unique value here. So, but you can't do it here because when you use width, that's for constants. These are constants. So you have, these two are constants, and they cannot be chained. So, for example, this you can do, this is what you want, right? Unique is a unique symbol. Then here you call unique, but that doesn't work because width cannot be chained. So in order to do that, you need to nest width. Yeah, annoying. It can be chained, but only on the latest version of Wolfram language, like released just about 3 months ago. Not in my version. My version is like 2 years old. I need to update, but I haven't yet. So anyway, so let's just do it the more plain way. So that is a local constant, unique. Then let's do another width. Okay. Then here, then here you can do this. Okay, so delete that, paste that, delete that. There. Okay, then whatever expression. So now we just put the expression there. Okay, so do you guys see what I'm saying? Do you guys see what I'm doing? Okay, so here, so there with that's one local constant. Then we use that local constant here, there, unique. Okay, then then we can combine like this or this. Okay, that's one step done. So we generate a unique number. Now once you generate unique, you need to remove it. Okay, so let's remove it. So after the whole result, Let's see. You see, Wolfram language is full of these nestings. Okay, so after this result, you want to delete those unique. Okay, then you can say delete cases something, and what you want to delete, you want to delete the unique constant. Okay, and something is that. Okay, so do you guys see what I'm doing? Okay, that should work. Should. Okay, so if we run this code, now we don't need this. If we run this code, it will not contain the 0, 0, 0. Okay, so in this case, it's 1, 2, 3, 4, 6, 7, 8, 9. Okay, run it. Let's see. 1, 2, 3, 4, 6, 7, 8, 9, right? So, but if we copy it, let's say 1, 1. Wait. Okay, so 1, 1 is that value. So the neighbors are 2, 4, 5. So it'll just return 2, 4, 5, not 0, 0, 0, something, 2 zeros, you know. So let's run it. Run it. Fantastic and beautiful. Okay, so that's the example output. Let's copy it. Let's paste the sample output here so you can see we improved the code by quite a lot. Okay, we use the width, which is creating local constants instead of instead of using block, which is creating local dynamic variables of dynamic scope. That's what block is. So we used local constant and we create a intermittent unique value, then we remove them. So now this code seems to work well, right? Right, we use the unique. Okay, so now we can further improve it because unique is very it's kind of slow because it generates a new symbol, unique symbol in the current session, and it tends to increase memory usage, for a long time. Anyway, let's leave it. So this now, so now the documentation, we can say when the cell is on the edge of the matrix, the neighbors outside of the matrix is considered 0. Now we can remove that because we don't have that problem anymore. Okay, so this is good. So let's say what we want to change that to 1. The result is 2, 4, 5. 2, 4, 5. Okay, that's like better example. Okay, so this function getNeighbors, is that right? Yeah. Now each time this function is called, it actually call array pad. So it is not the most efficient, but because every time it's called on a particular cell, it creates an entire array pad. So if the given array is, let's say, 1000 by 1000, then you want to find the neighbor of one single cell, then it's going to like generate the whole 1000 by 1000 array. In fact, 1002 by 1002 array. Huge. Right? So it's not very efficient. Yeah, but that's the beauty of this, because this avoid you having to manually check the boundary. Like whenever you have a row and column, if they are on the edge, you need to, you need to make sure you don't try to get an element beyond the boundary. So this is array padding, very convenient. That's a beauty of the Wolfram language. And here we use tuples to generate all possible neighbor indexes. That's another very powerful feature, you see. So as far as advent of a code goes, this code is just fine. But you don't want to use this in real life 1000 by 1000 arrays, especially when you need to call getNeighbors multiple times in a loop, because you need to know, you need to check every cell. So let's think of again, okay? So this function gets the neighbors. Are there a more efficient way? Of course, one way is just manually make sure the index doesn't go out of bound. But is there other, like, more automatic way like this, but more efficient? So we are just exploring. Okay, this is gonna slow down, like almost we are doing nothing, but let's do this exploration because that's a very good way to learn about things about Wolfram language. So you can so you want to get the neighbors, okay? Our code works, but not that one, but this one. Our code works, but is there even better way? That's the question. Is there even a better way to get neighbor? The other thing worth mentioning is that our function can work on arbitrary dimensional matrix. What you need to do, actually, you need to amend it a little bit. You need to do here is row column. You see, this row and column, right now this function only works on two-dimensional matrix. You need two indexes to specify any given position in a matrix. Now, what if you have three-dimensional matrix? The neighbor concept also works in any dimensional matrix, can be 4-dimensional, 5 or 1000 dimension. Okay, the neighbor concept of a cell always works. So you want to, you may want to make your function works for any arbitrary dimensional matrix, 3D matrix. So you need to, in the case of 3D matrix, you have row, column, and another index. Okay, so when the matrix is dimensional 3 or higher, you don't say row and column anymore. You say like I1, index 1, index 2, index 3, index 4. So you need n indexes for n-dimensional matrix. Okay, so if you actually write a function, for example, let's just for example, matrix and ijk. So for three-dimensional matrix, you would have a core syntax, something like that. Okay, and for four-dimensional matrix, ijk L, you have 4 indexes. So in general, if your matrix n d, okay, let's say matrix 3D. Wait, 3D. Okay, so 4D, right? So ND, then you're gonna just have a list of indexes. You see, you guys see what I'm doing? So in our case, if it's 2D, in our case, wait. Right now, our code is doing this. Okay, that's what our code is doing. And when it comes to 3D, you want that form. So it's better to have a list to. So this is like 1 unit because that's a list of indexes. This is 1 unit. So in general, you should make the syntax to be like that. Okay, so that works for any matrix of any dimension. Okay, but right now we are hard coding it for 2-dimensional. So but once you have 3-dimensional or 4-dimensional or n-dimensional matrices, then you see this row column doesn't work anymore. So you have the generalized, the first item in a list of the list of indexes, the first item, the second item, the third item. So then you can, over here, instead of row column, you use like a range to systematically generate all the possible indexes, +1 or -1. So they will form all possible indexes around that neighbor. Okay, that's what I'm saying. Okay, so but should we actually write such a matrix? Well, we can. It's not too difficult, but then we are getting away from solving the advanced code. So let's not do that. So let us right now just put some comment. We can make our getNeighbor function more general, so it works on matrix of any dimension. Okay, what you need to do is of the following form. Okay, so that's some kind of just comment. Okay, so let's cut. This is our current form. Better form would be that. So it can be generalized because the second parameter is a list of indexes. Okay, so that does that make sense, this comment? Okay, let's cut that comment, put it back, and we can make a comment here, Wolfram Language, paste that. Okay, now this is actually from yesterday. So if you know what I'm talking about, this is yesterday's advanced code, but we are doing, this is yesterday, so we need to cut that. So yesterday is episode 729. Today is episode 730. So let's put today's here. Show in browser. Yeah, so we are talking about generalizing this function for any dimensional matrix. Okay, so that's one idea, but let's go back here. So yesterday's talk show, we also fixed our code so that we actually improved our code. Yeah, we improved our code here. So that should be moved to today. So why don't we, let's see. Yeah, why don't we move this to today's? Wait, are you sure is this part? No, that's not that part. Yeah. Let's run it just to make sure this is working correct. Okay, now put it back. Now cut out that entire block. Syntax color the whole page. Go back to today's talk show. Open it. Then paste the new code here. Now syntax color the whole page, showing browser. So today's talk show, we talked about generalizing this function getNeighbors for arbitrary dimensional matrix. Okay, and here is our improved code. Okay, now next, let's move on to the next problems. I mean the next whatever we have to do. So now we want to make sure this actually correct. Okay, seems correct. I cannot pause. I don't see anything it might be wrong. So let's try to solve it. So yesterday we tried to solve it and we run into a problem. So let's see, copy the code. What were we doing? Yeah, we tried to solve it, but our answer is incorrect. Okay, so we copy the code, close, close. What is this to do? 279. This episode 729. Now go to today. Let's try to solve the problem. Start a Wolfram code, pop it out, and paste. Okay, that's the code from yesterday. And we have a new version of this getNeighbors. So let's clear it. Let's clear it. Okay, we got a new version. So this is what, 729. So go to talk show. This is today. So we got our new version, getNeighbors. Okay, so let's paste it there, and we don't need the examples. Okay, we got the code. So in the beginning we got this text, and this will turn this text into a matrix of 0 and 1. Let's run it. You see it returns. So let's see, it returns a matrix of 0 and 1. Okay, that represent this. Okay, okay, so far so good. Yeah, and let's put a comment so people can understand. Okay, then so this new, we named it matrix. Okay, so we turned it into a matrix, right? And now we define our function here. Okay, that's already tested. And next, what we want to do next, we want to apply the function to all possible indexes. So yeah, okay, so okay, let's define it here. Okay, so let's go to Wolfram Language notebook. Okay, let's make a copy of that so people can see. Okay, so now select or paste. Oh, not that. it made a copy. It pasted the image. Okay, so but we want this code. Copy, paste. Okay, Shift Enter. There is a result. Fantastic. Now next, we define our neighbors function. Copy, paste, Shift Enter. Okay, we define getNeighbors function. And now dimensions matrix. Dimensions matrix returns the paste. It should return 10 by 10 because there's this input is 10 by 10. Shift Enter, 10 by 10. Okay. Copy back here. So dimension matrix is 10 by 10. Dimension of the matrix. Now you just you want to generate all the indexes of the matrix for every cell. Okay, that's what you do. This. Okay, so here we hard coded the 10, but we can make it not hard coded. So what you do is for example, let me show you this. Okay, so you can paste. Now range at 10 just returns a list of 1, 2, 3, 4, 5 up to 10. So you got 1 to 10 and 1 to 10, and that just return all the Cartesian combinations, Cartesian product, 1, 1, 1, 2, 1, 3, and so on, and 2, 1, 2, 3, 2, 2, 4, and so on. See? So, but this 10 is hard coded. So instead, you should just say tuples add the dimension 10, 10. Okay, that will give you exactly the same result. So let's go back here, paste it, Shift Enter. Oh. Non-atomic expression expected. So which one goes far? Wait, so why is it? Oh, you need, okay, so you need, okay. So what you need is you need to apply range map at the matrix. Okay, then parentheses. Wait, so dimensions. Okay, so here is what you need to do. Okay, so basically like that. Paste. So let me double check on the operator precedence. Okay, so this part, okay, dimension and matrix that get computed first, then range map to that. So you get 1 to 10 and 1 to 10 a nested list. Then you need to add. Okay, add means replace the head. Okay, you guys probably don't know what I'm saying, so not add, just add. Okay, so let's delete that. There it is. Okay, so basically just that. Okay, let's do it again. Select all, paste it, Shift Enter. So this way we don't have hard-coded numbers like the magic number 10. Okay, so that's what that is. So delete that. If you are wondering what is that /add, that just means, let me show you. Okay, so if you have any function f/add bbb, okay, so if you have any syntax aaa/add bbb, that is a syntactical shortcut for map aabbb. Okay, so these two are equivalent because whenever Wolfram language sees that, it automatically transform it to this map something. So this is just a syntactical shortcut. and we are using it here. And this add, so let me introduce you guys the syntactical shortcut. So you see that add. So whenever you have something add something, that just means a square bracket BBB. Okay, actually we can run it. You see, it returns that. And this, you can also run it. Oh, wait, well, yeah, it returns BBB because that's what this return, because B needs to be a list. Okay, so, but yeah, so B, the BBB part needs to be a list. But anyway, these two are equivalent. Okay. Shortcut syntax. Okay, so is same as same. Okay, and that is same as that. Okay, so let me just put that out so that people know. Put it back. So create a new one, Wolfram language, paste it there. Okay, syntax color the whole thing, show in browser. So we covered we covered shortcut syntax. Now on this shortcut syntax, let me show you my tutorial that explains the whole thing about it. Wolfram language for programmers, search for it, you'll find it. Then you go down, so you'll learn that. So data structure, advanced, symbol, principles, full form. Okay, so there, so this part is kind of advanced. It explains how the whole Wolfram language syntax works. Okay. In fact, the entire Wolfram language is of this form, nested form: a symbol, square bracket, then inside it, symbol, comma, and they can be nested in any way. Any symbol can be any one of these forms. So that's the entire Wolfram language syntax. But then you got shortcuts. So because it's very inconvenient, whenever you say 3 plus 4, you have to say plus bracket 3 comma 4. So, but you can just write 3 plus 4. So how does that work? That works because of the syntactical shortcuts. So to understand that, you can to get the entire list of such syntactical shortcut, you can check out this page, Wolfram syntax shortcuts and operators. Okay, so 3 plus 4 is a short syntax for plus square bracket 3 comma 4. Okay, similarly for all these equality or greater than, so on the left hand side is the full form syntax. Okay, so what about the things I was just talking about, the add sign, for example? So for example, when we were talking about this, tuple, right? So we were talking about tuple add and this slash add. Those are also shown here. So you can see if you scroll down, expression separator in interactive session, pure function, you can see f at x is the shortcut for f square bracket x. Okay, and f slash at x is a shortcut syntax for map fx. So you see that, so you got all many other syntactical shortcuts. They are cryptic, of course, so when you became familiar with Wolfram language, you often use them. But I avoid using them because they are cryptic, otherwise most people wouldn't know, because they are not, Wolfram language is not based on C syntax, which is used in C++, Java, Rust, JavaScript, Python, everything. So usually I avoid this, but except kind of the add sign and /add is one of the most commonly used. Okay. So anyway, that's about the syntactical shortcuts. Now let's get back to our to solve these problems. So okay. So syntactical shortcuts, yeah, copy that. Let me paste the link here so I can. So there is some example. Okay, Wolfram Language syntax shortcuts. So now, so where are we? So now we define the function. Yeah, now let's continue to work on the advance of code. We turn that into a matrix of ones and zeros, and we define the getNeighbors function. Should be very good. Okay, then we get the matrix, the input dimension of the matrix. Then we created this should be called all possible indexes. Okay, so that's equals to that. Okay, and effectively this is what it returns, all possible indexes. Okay, then you see, so if you copy that, so basically that, but so let's see how well paste it. Okay, anyway, so that's all possible indexes. Then basically you want to apply getNeighbors to all of them. So what you can do is you simply map. Actually, we are doing that here. So you see we took, so we okay, so how do I explain this? So you see the all possible indexes is here. So we don't need this tuple anymore. We just say all possible indexes. So we are mapping a function. So ignore the first line first. Okay, ignore that line. We are mapping this function to these all possible indexes. And this function getNeighbors. So we get neighbors of our matrix. Then we, this function x is the parameter. So then you take the first part of x, which is the first index, then the last part of the index, which is the last index. For example, we can try it. So for example, let's say, well, actually, there's an example there. So copy that 99. Okay, so let's see. Paste it 99. Shift enter. So 11111. So that's matrix. That's 99. So where is 99? Let's go up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is here. So 99 is this one. So you should have 11111. 1111151. So is that right? 11111. That's correct. Okay. But I want to make a modification. Now remember we talked about before where if you want to make this getNeighbors function to be more general so that it works on any dimensional matrix, the better form is to have the indexes parameter as one single thing, as a list. You see, we explained here. And now, in fact, we run into that problem because here we write a function x. We want to apply this function to all possible indexes, any one of these 72, 73, 74, right? So the function takes, the function gets an argument x. Then here you need to separate because the getNeighbors takes takes them as two separate arguments. So that is no good. This is not the right style in Wolfram language. or in all the languages like Python, even Lisp, C, C++, Java, you tend to you don't make this kind of unit. You like whenever you write a function, it's just separate arguments. Even though for this function, let me explain this. Okay, so for this function getNeighbors, you have parameters, right? The first thing is the matrix, the input matrix. The second thing you want is the indexes for a particular position of the matrix. Now, if you think about it, the indexes should be one unit, right? It doesn't make sense if you just have one of them, row or just column. They are like, from a logical mathematical point of view, they are one unit. So why don't you so as far as code clarity goes, these two should be like a list of things, not just separate argument. They should be one argument because they always come together. Especially if your matrix is three-dimensional, then the index is 3 items, right? They are indexed. They cannot do without each other. They should be one unit. But in all other languages, in Lisp, in JavaScript, in Java, in C, in Python, in whatever, Ruby, Perl, you almost never do that. You don't do it just for the sake of clarity. You change the function parameters so that they become a list. Then you fit. You never do that. But you should, typically in Wolfram language. So that is why now I'm going to make a modification of our getNeighbors so it has improved form. Okay, did I miss a lot of comments? Okay, so yeah, so let me answer it in a minute. Okay, awesome keyboard. This is Ultimate Hacking Keyboard 80, UHK 80. I have a video review about last month. Check it out. I probably answered your question 20 minutes late. So Coffee Heart says, yes, I'm setting it up on my PC again. Another alternative to Wolfram is GNU Octave. No, not really. GNU. Let me explain that one. GNU Octave is a clone of MATLAB, basically. Am I correct? Yeah, something like that. I'm pretty sure it's like the open source, because MATLAB is a numerical computing software designed, focused with linear algebra applications. So if you have to do a lot linear algebra, matrices, MATLAB is a commercial product. Then about 15 years ago or 20 years ago, the open source people, the GNU, they created GNU Octave. They basically clone of MATLAB. They write it from scratch. But essentially, the semantics, the syntax is like a copy of MATLAB. Okay, so they okay, we can look up this Wikipedia. Okay, GNU Octave. So let's go Wikipedia. You see MATLAB. Okay, compatible with MATLAB. Basically, a clone, or in other words, in a unpleasant but more direct way to say it, it's stole. Okay, it's stole from MATLAB. MATLAB is proprietary. These GNU people, Free Software Foundation or open source, they don't like it. They don't want to pay. So they steal. They just copy it without copying the code. They can code it, but basically they copy the whole design. Design is actually the most, it takes the most effort to come up with a system, but they stole it. Okay, in other words. Okay, so that's a background. That's a GNU Octave. So when did it begin? 1993. Oh, wow. Okay, so much earlier then. much earlier. I didn't realize it's that early. Okay, so anyway, it's like a clone of MATLAB. Okay, so syntax and everything is similar, and it says mostly compatible, right? So, but how is MATLAB? MATLAB back in even today, there's no comparison to Wolfram language. Okay, MATLAB is focused on numerical computation. Okay, let me explain this. So you open MATLAB. MATLAB, that's their logo, very well known. So it's a proprietary multi-paradigm programming language and numerical computing environment. Okay, developed by MathWorks, which originally they are from Canada. Okay. Anyway, I have long experience with these programs back in 90s, and So anyway, my point is MATLAB is mostly a numerical computing software, focusing mostly numerical and linear algebra. Okay, that's the focus. So it doesn't do symbolic computation. It doesn't do symbolic integrals. Today it might do some, but it's not its focus. It doesn't do neural networks, artificial intelligence, and because over 30 years there's so many other things going on. So even back 30 years ago, when you compare MATLAB to Wolfram language, there's no comparison. Okay, they are in different category. MATLAB is mostly numerical. Wolfram language is symbolic. You can do symbolic solve equations or matrices in symbolically, and it also can do numerically. Okay, so they are kind of in different category. And if you must say which one is better, Mathematica, Wolfram language is like far more general. Okay, so that's that's the situation. So when you say alternative to Wolfram is GNU Octave, no, that's like a joke. Okay, so you guys don't know, so I'm telling you guys. Oh, never mind. Wait, so what are you guys? Awesome keyboard. So your review, that's great. So perhaps not as popular due to not having as much reach, but it's a great alternative for hobbyists. Yeah, that's not bad, especially GNU. This open source. It's open source, so it's free. That's the most important. That's the most practical reason. You can just download it and try play with it, right? So yeah, but I don't. You get what you want. You get what you pay for. Just like Linux. Linux is also free, but then you have to spend. You have to know how to do a lot of things. Like you format your drive. You have to reformat your drive to ex4, whatever. Most people don't know what that is. Then you have to, what distro are you using? What you must switch to Wayland. Oh, but there's a bug in Wayland or something. It's you can make an Octave notebook using Anaconda. Okay, yeah, it's too complex. Anaconda is this Python thing. Python huge library is like 4 gigabytes that combines all Python's libraries for scientific computation, for linear algebra, for numerical computation. It tries to do everything on a contra, okay? But again, there's no comparison. If you want a coherent, the most powerful programming language or app, a system for anything possible in computation, okay, there's nothing compared to Wolfram language, okay? Okay, that's kind of digression. So let's get back to this. Okay, let me quickly. Oh God, I digressed so much. We haven't been doing the event code. Let me quickly now get back to this, and we want to modify this function getNeighbors so that instead of taking separate argument, it's just the 1 unit of indexes for the matrix. Okay, so let's do that. So row column, so that's a documentation. Let's change that, and also let's change that here. So make a list. So this is symbolic. This is a pattern actually. So that's what we do. just 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 make it a list here. And in fact, that's all we need to change. Yeah, that's all we need to change. And are you sure? Yes. Then later on, if you want to make this work for three-dimensional, then you instead of that, you just say a list. Okay, then you also have to change this part because anyway. So we change that, and here then we make also change here, so you no longer have to say first x last x because this x is the input. Now you just say x. Okay, so just x. It's a list of two items, the indexes, column and row and column. Okay, so we got dimensions, we got all possible indexes. Then do we have that set? Let's write it. Let's define it. We didn't define our function. Okay, so I mean we didn't define our new modification. So let's do that. Hold on a second. So remove that and comment that out. Wait, okay, comment that out. Yeah. What? Shit. Okay, so that's our whole program. So we can run the whole thing. Let's see, starting from the above. So copy it, go back to Wolfram language. Now select all, paste to override, and shift enter. Fantastic. So that's our matrix. Matrix. This is the dimension 10 by 10. And here is all possible indexes of this matrix. And here is all the neighbors of the each cell. Okay, fantastic and beautiful. All the neighbors of each cell. So there are 100 of them because 10 by 10, right? And then you just sum it up. So all you have to do. So let me try it again. Oh, okay, wait. So all you have to do is you map this function. So map x if total x is less than 4, then you say it's 1. Otherwise 0. So now this is a function. Okay, you /add map that function to this output, which is the neighbors list. Okay, so what do you get? So let's try it. Copy it back to Wolfram notebook. Go here, paste it. Please make it work. Fantastic. So each cell becomes a number because if total neighbor is less than 4, then it's 1 special, meaning that cell is accessible according to the advent of code ELF story. So if it's not less than 4, it's 0. So you got this special. So what is the total? Total at %sign means the last output means this. Okay, so shift enter. 19, which is incorrect because yesterday we saw we saw that it should be 13, so we need to figure out. So we run into this bug just like yesterday. Shit, very annoying. This is kind of annoying to debug. Can you guys see it? Like here, right? Yeah, now you can see it. So according to the advent of code, the proper solution, the correct solution is 13. 13, not 19. How did I get 19? So So what you can do is you want to format this into, let me show you, partition. You want to format this output in groups of 10 so that you can kind of see this is a result. 1 0 1 1 1 1. So according to the result, that is not not right. So you want this axis. Wait, did I get it reversed or what? Less than 4. So what is this? So the forklift can only access a roll of paper if there are fewer than 4 rolls of paper on the 8 adjacent positions, right? So these neighbors, most of them has 8 entries, 1, 2, 3, 4, 5, 6, 7, 8, right? And some of them has 5 entries. That's because let's see, 1, 2, 3, 4, 5 when they are on the edge. 1, 2, 3, 4, 5, right? And then some of them has 3 neighbors when they are in a corner. So 3 is in a corner, 1, 2, 3, 4, 5. That's on the edge. That's on the edge. That's the top. This part is the first kind of the first row. Then you got 5. 1, 2, 3, 4, 5 on the edge, top. Then you got 3. That's the top right corner. Top right corner. So which is, this is incorrect. Top right corner. How many neighbors? It should be 2. So you got 1, 1, 1. This is incorrect. So we need to dive into details. So do you guys see what I'm saying? Do you guys understand? So let's work on the neighbors. Let's debug our code. So with this getNeighbors, actually we got a bug. So when you say getNeighbors, let's say 1, 1. Okay, so what do you get? 1, 1, the first entry. Paste, shift enter. What? Oh, not X. You got extra X. Paste, shift enter. 0, 1, 1. So the first part 0, 1, 1, that's correct. You see the leftmost this are the main code. So do you guys see what I'm saying? So the top left, that corner, it has 0, 1, 1 neighbor. That is correct. Now if you go second, 0, 1, 1, 1, 1. So the second is 0 on the left, then 1, 1, 1, 1. That's correct. What about the last part, the first one in the 10th column? The first row and 10th column. That's on the upper right corner. 1, 1, 1. 1, 1, 1. That seems correct. Okay. So what is the criteria? I must got the criteria wrong. So the forklifts can only access a roll of paper if there are fewer than 4 rolls of paper in the 8 adjacent positions. fewer than 4. That means less than 4, right? In 8 adjacent positions. Okay, if you can figure out which rows of paper the forklift can access, what if there are 0 rows of adjacent neighbor? There's no such occurrence, because if there is, then you need a box of dots. So I don't get it. Why is our code incorrect? So what if they? Oh, okay. Actually, you don't need. You don't need to compute all the indexes. All you need to is to compute the cell locations. That's a dot. So all you need to is to. That's right. That's right. Oh, that makes sense. So for example, this position, let's see. Let's say, can you guys see? So this is 10th row, 9th column, 10, 9. Okay. It has 2 neighbors, right? Above. However, does that count? According to me, it would. But according to this spec, which is kind of lousy, the cell that already is a row of paper does not count. Okay, so simple. So you don't want all possible indexes. You just want the ones that are already 0. Is that right? Yes. Okay, so let's fix that. So how do you do that? You can do that by cases. Okay, syntax completion. Okay, cases. Then you say X matrix. Okay, X matrix, that's my matrix. You want the cases of 0. Okay, now let's look up the documentation. Not matrix. Okay, the cases. Look up the documentation. Pattern gives a list of case elements that match this level spec. So what by default level spec is 1, I think. Now if you don't know what I'm saying, don't worry about it. Okay, cases use standard level, so the default value for level spec is 1. Yeah, just level 1, so you don't have to worry. So this will return all possible positions, their indexes, where 0 occur. So what? What? Oh, right. Then you okay. So you need right. So you don't want to use cases. You want to use position. Okay. So let me show you. Position will return all positions. Okay, of 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 a nested list where it matches 0, and you want it to apply a level 2 only. Okay, so let me show you that will work. Okay, so if you do that, that's the result. Okay, so you want to say, so not cases, so you want to say, so this is all so this is all indexes or indexes where the cell is empty. Okay, but what is the word advent of code uses to describe like empty? They didn't say. So either it's occupied by row of paper or it's not. So it's empty. Let's just say empty. So index of something like empty cells. Okay, let's just do that. Index of empty cells, okay, equals to that. Okay, so we can run this. Right? Fantastic. Now we can refer to that index of cells. We don't need that. Yeah, we don't need that. Index of cells here. Okay. Copy. I'm pretty sure it'll give us 13. Shift enter. Oh, then you need to total. Okay. Total at percent sign means the last output. Shift enter. 6. God, Jesus, we got fucked up. Oh, why is that? Why is that? Now it's 6, but the solution should be 13. Now, is there anyone watching? Nobody. Okay. You guys need to help me, okay? But unfortunately, nobody is here. I don't think so. Few people. In this example, there are 13 rows of paper that can be accessed by a forklift. Now, is there something I didn't understand? So is it true only... Wait. Look at this one, okay? Look at this example on the upper right corner. So it's got 3 neighbors that has row of paper. Oh, so now does it mean, so you see on the upper right corner, that cell got 3 rows of paper. So technically it qualified because you know, stupid available code, they format, you know, so because they, where does it say less than, fewer than 4 rows of paper, right? So on the upper right corner, you got that cell got 3 rows of paper. So that should count. But however, if you look at the diagram, it shows the solution. You know, that upper right corner is not one of it. So what does this mean? So we didn't understand the problem correctly. The forklifts can only access a row of paper if there are fewer than 4 rows of paper, fewer than 4. Okay, the upper right, it has 3. Is that fewer than 4? Yes. Okay, if you can figure out which rows of paper. Oh, what? Oh, you should deal with the cases where there's a row of paper, not the empty slot. Fucking idiotic, okay? So not empty cells, not index of empty cells. You want to work on the index of non-empty cells. Fucking stupid. So let's just okay, let's just try that. So instead of so this is easy. So instead, so it just, you can just say 1. Okay. Okay. Copy that and just replace that. Okay, that should return the answer. Okay, copy. Let's try it. Paste, shift enter. Okay, blah blah blah, and then total at percent sign 13. Fucking stupid problem. Okay, basically we solved the problem. Now we need to use our personal input. So 3 more minutes, we'll solve it. Okay, now clean up a little bit. So all possible indexes, that's not what you want. Indexes where empty cell is empty, that's not what you want. Indexes of non-empty cell, that's what you want. So in terms of the advent of code jargon, you say this is all indexes where the cell is a paper row. Okay, that's what you want. Then you just map apply, and then you just say total at, that's your result. Okay, so now we can actually copy all. Let's not output that. Okay, so let's copy all. Fantastic and beautiful. Select all, paste, shift enter. Wait. Okay, wait. You got the wrong answer at the end because of the operation precedence. You need to make this like that. Okay, select all, paste, shift enter. 13. Perfect. Okay, now back up. Now you need to get your own personal input. Okay, so where is our personal input? Search for text band of code 2025 day for personal input. Okay, this giant shit, copy it, close. Wait, don't close. But also, okay, move here. Then this is a list, huge list. Okay, and let's just say input equals to this. This. Did we hard code anything? No, but it should work. Yes, copy all. Go back here, select all, paste, shift enter. Oh, it's taking a while. Impossible. It's done. So this giant input, go down, giant input. We forgot to put a semicolon to suppress the output. So anyway, the result is 1527. Copy that. Back to advent of code. So paste 1527. Enter, submit. That's the right answer. You are one gold star closer. Thank you very much. We solved it. We solved it. So anyone watching, congratulate me. Okay, 7 concurrent viewers. So thank you guys for watching. We had fun. So let's clean up. We shut down in about 3 minutes. Let's just clean up. So there is a solution 1527. That's correct. So put it back. Syntax color the whole HTML page show in browser. So we modified our getNeighbors code so that it has the form where the second argument, which is a list of indexes, is more consistent. It comes in one unit for arbitrary dimensional matrix. We explained that part where, and then we also modified our getNeighbors code so that it's a bit more efficient, but still it's using array pad. So every time you call this function, it creates the whole array, padded array. So that's not efficient. Okay. So if this is a real life problem, you don't want to do this because you are going to call getNeighbors like hundreds of times or even millions of times. Each time it's called, it creates a whole array, padded array. So you don't want that. But you see, but that's a trade-off. You know, if you want convenience, if you want elegant code, this array pad is fantastic. So you don't have to like check if the current index is out of bound. It doesn't have the next neighbor, you know, things like that. Then we talked about the shortcut syntax of the Wolfram symbolic language, also known as formal language in computer science, where the source code is actually everything is just symbol. So you kind of treat it like a string. All you do is string manipulation or find and replace. That's how it computes. Okay. Syntax shortcuts. By the way, for Lisp fans, this is called meta expression as opposed to symbolic expression. Anyway, that's Lisp history. Okay. So syntax shortcuts, then we talked, then we finally solved the problem. Okay, so huge input. Okay, finally solved problem. We were wrong before because we are working on the wrong cells. You need to focus on the cells that's already occupied, like 1. Okay, bye guys. Thank you guys for watching. If you like my stuff, donate. Okay, go to xarli.info homepage. Here, XAR code, xarli.info. Go all the way down and you can Patreon me, okay? Do Patreon me and Amazon gift card me or PayPal me. Bye guys. Congratulations, GCS and Noob. Bye guys. Tomorrow we're gonna do part 2. Don't know how many millions of hours we're gonna